Good morning. Today is November 12th, Thursday, November 12th, and today is really the first day of Unit 7. Unit 7 is on exponential functions. And we talked Tuesday in class about how is an exponential function created, and we used the example of cutting paper where we took one piece of paper, we cut it in half, and then we cut the paper in half again, and then we cut the paper in half again, if you remember doing that, and we created a basic equation. Now with this basic equation, we refer to this as the initial number, and we refer to this as the rate. Now think of exponential functions as kind of like an umbrella. That's my umbrella. So this is exponential functions, abbreviated, and underneath that there's a few different types. There are specific types. You could specifically have one that's called exponential growth, and you've learned about that in Algebra 1, 2, and you could have one exponential decay, and then there's ones that fall into the category that are neither growth or decay. So we're just going to call those the others. So we're going to start learning about growth and decay. Now these others, by the way, do relate to growth and decay. They just have a reflection piece to them. So exponential growth. When they talk about exponential growth and decay, they use some really common word problems. So if I gave you time and I said, all right, I want you to Google exponential growth, that often would provide you with a word problem that talks about bacteria and how it multiplies over time. And bacteria, if you look into a petri dish and you look at the growth of the bacteria, it grows at a really fast pace, right? And so it looks something like this. It looks something like that. There's an initial amount and it continues to grow at a really fast pace. And then if you've ever talked about like buying a brand new car, and maybe some people have said, well, don't buy it brand new. Don't buy it right off the lot brand new, because as soon as you drive it off the lot, it's not worth the same. And for the majority of cars, that is true. Let me let this person into class. Looks like Steve's having a little difficulty with his internet today. This is called exponential decay, and it looks something like this. And the really common, again, the really common one is the value of a car after you take it off the lot. And it looks something like this. We have the value, we take it off the lot, it starts going down. Is that all cars? No, but the majority of cars. So this is the shape of exponential growth and decay. And if we take them out of the context of a word problem, it's looking like this. It's continuous. Again, I'll be writing all this down on a piece of paper as I go through this. This is an example of growth. It's continuous from left to right. From left to right, it rises. Decay is also continuous, but from left to right, it goes down. There's a decline in it. And if we think back to this original equation, this initial amount on a graph is known as the Y-intercept. So this would be the Y-intercept. That number would go here. And for this graph, that number would go here. Now the rate at which it grows from left to right would go into this position, and the rate at which it declines from left to right would go into this position. Now one thing that's important to know about exponential growth and exponential decay. For growth and decay, this initial number is always positive. For growth and decay, that initial number, the initial value, is always positive. Now, is there a way that you'd be able to look at an equation and go, oh, that's growth, or that's decay, or that's other? There is a way. So one is, if this is positive, there's a chance it could be growth or decay, right? It's growth or decay. If this is not positive, it goes into the other category. Now, how do we distinguish between growth and decay? Growth, this rate value, for growth, this number is greater than 1. It's not equal to 1, it's greater than 1. And for decay, we say that number is less than 1 but greater than 0. So it's not equal to 0, it's not equal to 1, it's in between, and then the growth is greater than 1. So if I come back up here, notice that this number for growth and decay will never be equal to 1. It's never equal to 1. It's either greater than 1 or between 0 and 1. And the number in front always has to be positive. That's for growth and decay. So let me write down a few problems here. And you're welcome just to watch these if you don't want to put these down. Give me 1 second to let in who's joining us late. So here's some examples. So let's classify this right now as exponential growth, decay, or other. Well, I know it's exponential because the variable is the variables in the exponent position. Because this is positive, this is initial number, I know it's either going to be growth or decay. Now 0.5, also known as 1/2, is between 0 and 1. This is an example of decay. Okay, because this is positive, I know it's growth or decay. Because this number is greater than 1, it'd be an example of growth. Again, it's exponential because the variable's in the exponent position. Okay, coming over here, this initial number is not positive. Automatically, I know it's neither growth or decay. Growth or decay. It's exponential, and we're going to talk about how it's actually a reflection of one of these two, but that'll come up a little later on in the lesson. Okay, again, this is not positive, so it's neither growth or decay. The first task today was providing you with several examples of equations, and you would just either classify them as growth, decay, or other. So again, why is this decay? Because it's positive and between 0 and 1. Positive and greater than 1. Now, just for practice, what if I covered up this negative sign? Okay, so it's positive and greater than 1. This would be growth. Positive, if I covered it up, and let's say it didn't exist, positive, greater than 1, this would be growth as well. That's the first learning task today. The second learning task is, what does this look like? What does this look like if we start to think about sketching them? So for each of the second task, we're going to do 3 things. We are going to identify the Y-intercept. We're going to identify the asymptote in the graph. We're going to sketch the graph. And then we're going to do the domain and range. Now everything goes back to you understanding that this is growth and this is decay. Notice this is getting closer and closer to the x-axis, but it'll never actually cross over. That's an asymptote we'll talk about. And this is getting closer and closer. We call it approaching. It's approaching the x-axis as well. Again, it will never touch or cross over unless we took and then we translate, unless the equation said we need to translate it down. Now, another word for x, or another equation for x-axis would be y equals 0. Again, we can call this the x-axis, but as an equation, it's y equals 0 because every point along this line has a y value of 0. 0, 0, 1, 0, 2, 0, 3, 0. Negative 1, 0, negative 2, 0, okay? All right, so let's look at the first problem. So here's our first problem. It is y equals 2 and 1/2 x. So the first thing that when I do when I look at this is I go, okay, I can see that this is an example of exponential function because the variable's up top. This number is positive, so it's either growth or decay. And because this number is between 0 to 1, I know it's going to be decay. Then in my mind, I'm like, what does decay look like again? So if I come over here, decay looks like this. From left to right, it declines. Now, there is no shift, and you're wondering, like, what does a shift look like? Well, we'll see that later on, not today, in the days ahead. A shift would be, a vertical shift would be like +3. There's no taking this function, we're going to rise up or go down. And for that reason today, all of our asymptotes will be on the x-axis. Give me 1 second. Somebody's joining us late. Okay, so what is the y-intercept? That's this initial value. So I go to +2, and I'm going to write it down as 0, 2. That's the y-intercept. I know that the asymptote is at y equals 0. I want you to write it as an equation, so y equals 0, the first two are done. Now the sketch just needs to look like this. So it goes through this point. As it goes to the right, it's getting closer and closer, or we use the word approaches the x-axis, and it comes from up top. So I've done the y-intercept, I've identified the equation asymptote, and I've sketched it. How do I know how to sketch it? Again, it needs to replicate, or it needs to model what a decay function looks like. Now the last thing is domain and range. The domain, there's no limit how far it goes to the left. Notice that as it goes to the left, it goes up, but there's no limit how far it goes to the left, and there's no limit how far it goes to the right, because it's a continuous function. The range, we always go from bottom to top, small number. So there's no part of the function down here. Now we know it approaches y equals 0, but it never touches that. And for that reason, we put a parenthesis. There's no limit how high it goes. Okay, we're going to practice that problem again. This time I'm going to do y equals 5 and 2 raised to the x. So first thing I'm looking at is I'm going, okay, it is exponential because the exponent is in the variable, the variable is in the exponent position. It is domain and range. So, oh my goodness, my words. It is growth or decay because this is a positive number. And because the rate is greater than 1, it is growth. Now what does growth look like? Growth looks like this. From left to right, it rises. So that's the basic shape I'm going to have. All right, let me draw a little graph here. Now how do we identify what the y-intercept is? Okay, y-intercept is right here at 5. 1, 2, 3, 4, 5. Okay, this is your y-intercept. And this is my rate that tells me how fast it goes up. Note that there is no additional numbers behind here, so that will be, this will be right here would be my asymptote equation y equals 0. I've identified the y-intercept and I've identified the asymptote with an equation. Now I sketch this basic shape. And now domain and range. So domain, no limit how far it goes to the left, no limit how far it goes to the right. Range, it comes from the bottom, it comes up, although it never touches 0, it's approaching it. And no limit how high it goes. I would like you, I'm going to give you a little bit of time here, I'd like you to do this problem. Following the 4 steps. Okay, you're going to do y-intercept, and then please for me do the y-intercept, the, what else do we have? The asymptote with the equation, the sketch, and then domain and range. Go ahead, please. I've identified the y-intercept. I've identified the equation of the asymptote. I've sketched the graph, the domain, no limits, continues from left to right. The range comes here, and again, it's above that, so it's 0 to infinity. Okay, hopefully you're feeling pretty good about that. We're going to go on to the next problem. And now this is the other category. Remember, within exponential functions, there's growth, decay, and there's the other. Now the other really, it's a form of it's a form of growth or decay. Let's do this first one. Please make sure you're writing this down with me. Remember, you're getting a condensed form because I am videotaping this, so I'm not taking time at this point to ask you, what are you understanding and what are you not understanding. So let's go back really quick here. The first task you had to do today would be I'd present you with an equation and you would say, is it growth, decay, or other? Now if this was the problem, you'd say other because this initial number is negative. Since this initial number is negative, we just say other. Okay? The second task is, can you sketch, identify the equation of the asymptote, the Y-intercept, and can you state the domain and range? And that's what we're doing right now. Now, here's how we're going to do this when that number in front is negative. When the number in front is negative, we're going to cover it up. We're going to pretend it does not exist. So if I said, what is this? You'd say, okay, it's positive, okay, so it's growth or decay, and because this number, the rate, is greater than 1, this is going to be a growth problem. So this is going to look like growth. Looks like this. From left to right, it rises. Okay, simple enough. So what does this negative in front do? This negative in front always takes this function that I just drew, and it takes it and it simply reflects it across the x-axis. So if you had to reflect across this line, that means I folded along this line and now the green would come straight down. It would look something like this, but I'm now going to do in orange. So my picture will now look like what we see in orange. That's the only difference. You cover it up and decide, is it growth or decay? And then whatever you decide, draw a little picture and then flip it. Flip it always across the x-axis. So how do we officially do this? This still represents the initial value. So if this is -1, here is a -0.5. And whether you write it as a decimal or equivalent fraction, that's up to you. And again, we do not have, at this point, we do not have any type of a vertical shift. And a great question may be like, well, what would that look like? How would I know if there was a vertical shift? That means you'd have some number in back, like a -1 or a +10. There's no shifting of taking this graph and moving it up or down, and for that reason, we'll always have the asymptote at y = 0. Now that will change when we start to shift this thing up and down, left or right, but at this time, no. Give me 1 second. Okay. So I've got this done, I've got this done. Now I need to make this shape. Okay, good. Now domain and range. No limit how far it goes to the left or to the right. Now remember, this is where a lot of students do make a mistake here. Students think that, okay, which way do I go? It's always, remember, from the negative to the positive. So negative, there's no limit how low it goes, and it approaches 0. Approaches, never touches it. Would it be wrong if you did it like this? Yeah, that would be wrong. Okay, it's the negative first towards the positive. Okay. Give me a second. So I've done all 4 of those. I'm going to have you practice this one right now. And I'll give you a minute or so to carry out those 4 tasks. Y-intercept, equation of asymptote, sketch, and then domain and range. Okay, so I'm going to cover up the negative and go, okay, it's positive, and because the rate is between 0 and 1, I know it's decay. What does decay look like? From left to right, it goes down. But now when I add in that negative out front, it's going to reflect across the x-axis. So it's something like the orange line that I currently have. This still represents our initial value, 0 and -3. The rate tells us how fast it's going to drop here if I look at this at the reverse way. So I'm going to make the shape just like this. Again, because I don't see any numbers in back, I know that we have the same horizontal asymptote with the equation y = 0. And now I'm going to do the domain and the range. No limit how far it goes to the left or to the right. It's continuous. And for the range, always bottom first. There's no limit how low it goes, and it approaches 0. Okay, so we finished up our second task. Let's move on right now to our third and final task today, and that is, how can we solve exponential equations? I will say that if the PowerPoint would have been working today, all the problems that I previously created had what I call pretty answers. Answers that look like 2, -2, 1/2, 1/3. They're nice fractions or nice integers. What we're going to see today in our answers, since I've just previously completed these problems with 0 hour, is that the answers that we're going to get are not pretty. And when we check the solutions, we'll be able to see if it works or not. But know that when you do your homework, it's going to be a little bit simpler. Okay, here we go. As I shared with you in the last unit, coming back from fall break, one of the first things we did is we created this table for unit 6. And I said we're going to be using this table continuously. Make sure it's in your notes. If you haven't done that and you need a copy of this, you need to reach out to me because this will be continuously being used. Okay, what we're going to do today is we're going to look at the base numbers, and we're going to find out which row contains those base numbers. So I'm looking for 9 and 27. So there's ones 9 and 27. They're going to be in the exact same row. There's a 9 and there's a 27. So I'm going to rewrite 9, that's the goal of this, as 3 squared. And I'm going to rewrite 27 as 3 cubed. Okay, so there's the 9 and there's the 27. And now I need to bring down what was already there as the exponent. When I bring it down, it should be in parentheses, because we don't want this 2 to only be applied to the 2x. It should be applied to everything, so also to the -1. And without those parentheses, that wouldn't happen. Now, why do we do that? Because if you remember, let me go back here, just trying to give you a little side idea. If you remember when we had something like this, I'm going to make this up. When we learned about rational, that was actually in Unit 5, about rational equations, I said when you have an equal sign, so we have an equation, and we're solving, and we get the denominators all the same, we get to cross them out, and we only have to solve the top. Okay? It's kind of like a shortcut method. That's basically what this is. When we have the bases exactly the same, and there's no extras, there's no like +2 or -10, it's a base and an exponent equals a base and an exponent. That's it. When the bases are exactly the same, we get to cross them out and solve. Now I'm going to distribute, and I get 4x minus 2 equals 3x. And then at this point, you get to move the x's to one side. You get to choose, and the constants the other side. Totally up to you which side you move them to. This may be the only pretty answer that I created today out of the others. So I get x equals 2, but we don't know if that's correct or not. So what we need to do right now is we need to check for extraneous solutions. So it's possible, for instance, that you do all the work and you get an answer, and your work is right, but when you plug it back in, it doesn't work. You'll know it does not work if, when you substitute this answer in for x and you get a value on the left, and you substitute this answer in for x on the right, you get a value on the right. When these two don't equal each other, it means this is not an answer. It's extraneous solution. So I'm going to show you right now how do we check for that. So I'm going to go into Desmos, and I'm going to start by plugging in. Remember, it was 9 raised to the 2, and I'm going to change the x. This was the exponent, right? So I'm going to come over here, and I'm going to change this to a 2, and it does the math for me. Okay, so that means that when I substitute in, and remember this is an easier problem, they're going to be more complex with uglier answers. When I substituted 2 in, we get an answer of 3. And we could have done mental math. 2 times 2 is 4, minus 1 is 3. Okay, got it. So I'm going to come back here. Okay, so I get an answer of 3. So I'm going to do 9. This is your A to the B. This is how you get to the next A. 9 to the third. Right, and then I'm going to click down below, and the next one was 27. Again, we got an answer of 2. That may be really confusing to you. So 27 to the second better be equal to 9 to the third. Those two better equal one another if that is the correct answer. And I can see they do equal each other. That means the answer I was able to achieve mathematically using algebra is correct. This is the correct answer. Okay, we're going to go on to the next problem. Okay, here we go. I can promise you that this answer, although it is correct, we can get an answer, is just not as pretty. So hold tight here. I'll give you a chance to write it down. First thing you're going to do is you're going to find that table in your notes. And I'm going to find a line, a horizontal line that has 16 and 1024. There's 16, there's 1024. I'm going to rewrite 16 as 4 squared. I'm going to rewrite 1024 as 4 to the 5th. And then whatever was there in the exponent position should go in parentheses. When these bases are the same, that's the shortcut. You get to cancel them out. And now I could solve 16x minus 2 equals 5x minus 25. Here's an example of an ugly answer. Now, is it correct? Let's check. Let's check if this is really the answer. So I'm first going to plug this in right here. I'm going to forget about the 16. I'm going to plug this in and get an answer up here in the exponent position. And then let's just pretend. I'm going to make this up. This is not true. Let's say after I plug this in and I get an answer of like 20. I know that's not true. But let's say I get an answer of 20. Then I'm going to plug in 16 to the 20th. Okay? Then I'll plug this in, get an answer, and plug in 1024 to whatever that number is to see, are the two values on the left and the right equal? If they are, this is the correct answer. If they're not, this is extraneous. That means there'd be no solution. So right now I have, at the very top, I have 8x minus 1. So I'm going to come up here. Remember, 8, here we go. 8x minus 1, but I don't want an x. I want negative 23 divided by 11. Okay, that's really ugly. We need to be precise with our answers, which means we don't round unless it tells us to do so. So I'm going to click here. Okay, so I know that I want 16. I want 16 raised to whatever value right now is in decimals. That means on the left-hand side there is a value of, although it may be very ugly, okay, that's what we have on the left. If negative 23 over 11 is correct, we'll find out in just a second. Now that I have x subtract, really, but it's negative 23 divided by 11. Oops, excuse me. That was on to the next one. Negative 23 over 11, subtract 5. Oh, it's important here that I'm looking at the screen at the same time I'm typing. You do have to use the tab key to bump up instead of it being in the denominator. And if you're a little confused, where is she getting this? That's my answer. And then I'm subtracting 5 from it. That's my answer. And I'm going to subtract 5 from it. So I'm going to take 1024 raised to whatever value I'm getting right now. 1024 raised to whatever that value is. Oh, ugly again. So I click on fraction because I can't round. And now I do 1024. A to the b helps me raise it up. Negative 78 divided by 11. Now I'm going to cross this out and look at these two and compare them. These have to be exactly the same, and they are, which is able to prove to me that this is the correct answer. You're going to do the next one with me. I'm not going to give you enough time to probably get it all done, but let's see how far you can get. Give me a second here. Okay. 2 raised to 7x plus 3 equals 16 raised to x minus 3. All right, I'm going to let you look in your notes and look at that table and decide how can you rewrite 2 and 16 so they're the same base. I'll give you a minute to get started before I begin. If you're confused, what I'm trying to have you look to do as the first step is I'm looking at the bases of 2 and 16. I go to the table, I go across 2 and 16. Nothing in that row. 2 and 6. Oh, there's a 2 and 16. Now, some students in the past have said, but I see a 16 here, but there's no 2 in that row. Let me just let in the next person. Just doing this here. So it has to have both a 2 and a 16 in the same row. So this is 2 to the first, and this is 2 to the fourth. So 2 to the first and 2 to the fourth. And I'm going to give you another 30 seconds to see if you're able to come up with an answer before we check it together. Once you get an answer, if it's done in the next 30 seconds, please go into the chat, put the number down. I see some people are trying to get an answer here, but I see a couple different answers, so let's -5. Oh, it's a pretty answer. It's pretty easy, right? Not an ugly fraction, a nice integer. So let's check to see if it's right. Just because it's a nice answer doesn't mean it's going to work. So I'm going to do, let's see if I can do some simple math here. I know 7 times -5. 7 times -5 is -35. And if I add 3 to that, -35 and 3 is -32. So I'm going to come to this position, and I'm going to type in 2 raised to the -32. Oops, excuse me. -32. Then I'll go on to the next one. If I come back here, I know that if I substitute -5, then -5 minus 3, -5 minus 3 is -8. So I want to do 16 to the -8. I don't have to write these answers down. So in past year, students say, what do I do with this answer? You don't have to write it down. We just want to know, are these two answers exactly the same? I'm looking them over. They're identical, which means that is the correct answer. That means -5 is correct. Let's do one more. And let's make it a little bit harder in strength. One second, please. Okay, I'm going to clear this off here. We're ready for the next problem. Okay, this problem. Now I'm looking again at this chart, and I'm looking which row has both a 16 and an 8. And you may be thinking, Miss Bradley, it's not an 8, it's 1 over 8. When you have 1 over number, forget about that. We're going to come back to that at the end. So I'm looking for just a 16 and an 8. A 16 and an 8 have to both be in the same line. 16, oh, there's a 16 and an 8. So I'm going to rewrite this as 2 to the third and 2 to the fourth. 2 to the third is 8, 2 to the fourth is 16. 2 to the fourth is 16, 2 to the third is 8. Now, 2 to the third is 8. It's not 1 over 8. Remember that when you have 1 over a number, you can represent that by simply making that exponent negative. So when I find it, how do I rewrite it? I'm looking at just 8, and then to account for 1 over that number, I add a negative in front of it. Okay, like always here, I have bases that are the same. And now I'm going to solve. Now, just because it's an ugly answer of -7/20 doesn't mean it's wrong. So I'm going to bring that up here. I'm not going to do that in my head. I'm going to take -7/20 plus 5, get the answer, and then take 16 and raise it to that. Once again, I'm going to take -7/20, add 5, get that value, and take 16 and raise it to it. This is my last problem. Stay with me. So -7 divided by and now to that I'm going to go up plus 5, and I'm going to turn that into a fraction. Okay, 93/20, 16 raised to the 93 divided by 20. All right. So that's the left-hand side. Let's look at the right-hand side. Right-hand side, I just need to type in 1/8 and then raise it to this fraction. Yeah, you can't see?
No, isn't it -20/7?
Yes, it is. Yes, it is. Thank you. Good call. Let me bring this back up here. Was that Jocelyn? No, whose voice was that? Thank you for finding that mistake. So the math here was right, but what I did is I should have divided by -7 because I'm trying to isolate the x. And then going fast, I make a simple mistake here. So divide by -7. Once again, thank you to the person who just found my mistake. And so now the x is isolated, and I have 20/7. Let's try this. Let's go back here and reverse it. I'm going to start with this side since I'm almost done. So I'm going to start with the right-hand side. Thank you again to the person who found my mistake. I'm going to take 1/8 and raise it to the 20/7. So that is right here, okay? And then I have -20 divided by 7 plus 5, and I need to take that and raise 16 to that. A to the b raises it. 15 divided by 7. I'm going to erase this, and now this is, if I pull up, this is my right side, this is my left side. They are equal, which makes this the correct answer. Now, if I would have plugged this one in, and somebody would not have spoken up, thank you again to the student who spoke up, we'd have seen that the left side doesn't equal the right side, and I would have assumed that it was extraneous, when in reality it was just a simple math mistake that I had made, okay? This is the correct answer. Thank you once again for finding that mistake.